Asadallah masa'akum bi kulli khair. Welcome, everyone. My name is Maurice Pomerantz. I'm the Executive Director of the NYU Abu Dhabi Institute, which is an interdisciplinary center of advanced research, artistic creation, and public outreach. I'm also a professor of classical Arabic literature here at NYU Abu Dhabi. For those of you who it's your first time here, I'm delighted to welcome you to NYU Abu Dhabi. We continue to foster critical conversations about the most pressing issues of our time. Tonight's discussion is certainly part of that. It's part of our ongoing commitment to bringing some really world-class intellectuals and scholars here to educate us about some of the biggest issues facing us. Before we begin, I'd like to briefly mention two upcoming events that exemplify some of the range of topics that we explore here at the Institute, both in public lectures, and I don't know if some of you have also seen, there are a fair number of academic conferences going on here as well. On November 17th, Professor Michael R. Toms from Stanford University will address the timely question, is artificial intelligence a threat to democracy? That's also at 6 p.m. Here in this auditorium. He'll be drawing on experimental evidence about AI's potential to undermine democratic processes through misinformation and deepfakes. So very timely. Then on November 24th, it's our great pleasure and privilege to host the Nobel laureate in economics, Abhijit Banerjee, who will revisit his groundbreaking work, Poor Economics, 15 years later after its publication, reflecting on what we've learned about poverty alleviation through field experiments and how new challenges like COVID-19 and climate change are reshaping development economics. Now it's my sincere pleasure tonight to say that this talk is very much was a partnership between ourselves and the German embassy here in the UAE. And it's a partnership that really exemplifies a kind of, I think, something of our shared, but I can see very much in the German embassy as I was reading about all of the work they've done. On the one hand, I would say overseeing this relationship that spans trade, investment, cultural exchange, and collaboration, particularly on areas of sustainable development and innovation. The German embassy of the UAE the German embassy to the UAE has promoted significant academic partnerships as well. So, and we thank them for that and bringing Professor Levermann here tonight. And has also been very important, has done important work in areas such as renewable energy and hydrogen technology. So it's a commitment to education and a commitment to how education can address the pressing issues of our time, which when you hear something about the biography of our speaker, you will understand better. For now, it's my great pleasure to introduce Andreas Feil, the first secretary of the German embassy to the UAE. So thank you very much, and thank you to the German embassy again for helping us coordinate this event. So thank you.
Distinguished faculty members, dear students, dear Maurice, Professor Levermann, it's a great pleasure to welcome all of you here this evening. Let me explain a little bit how this idea to bring Professor Levermann to the UAE came into being. So I'm a person who likes to read popular science, and in particular about climate, because that's my work at the embassy, but also my personal passion. And most of the books that you read about climate, they either only mention the catastrophes that are awaiting us in the future, or they somehow try to deny the problem. But when I read Professor Levermann's book and the ideas that he is going to introduce us, I found something different, a way to think that is derived from mathematics and from chaos theory that finds a way to combine the imperatives of growth and the imperative of climate protection. Because I think it's undeniable that economic growth is a part of humanity and it's also necessary. And in July, I just did my first trip to an African country when I visited Uganda, and I saw still the potential that the whole developing world has and the necessity of enabling economic growth there, but ideally without exceeding the limits that the planet and physics are giving us. So at the moment, we feel that we are at the critical juncture in global climate politics. 2 years ago, the UAE consensus was adopted here in COP28, and there was great hope that now finally we have a roadmap to implement the Paris goals. But very quickly we saw that there's a huge backlash against global climate goals, which is most significant, I think, by the second withdrawal of the US of the Paris Agreement. And that's why we as the German embassy, we established this platform called Climate Talks. So Climate Talks is a series of events that are being organized on the whole planet by German embassies to bring together students, science, policymakers, private sector to discuss this pressing issue and to support and push for more ambitious climate goals. And it's through this initiative that we are inviting today Professor Levermann, and be prepared for some hard science. I already had the pleasure to listen to the lecture two times in the last 2 days, but it's really enlightening, and please stay until the end, because I think that for me personally, at least, the best part comes at the end. So fight your way through all the equations, and then you will be enlightened. So thank you so much again for coming, for being with us, and thanks for Professor Levermann for being here. And now it's my pleasure to hand over to you.
Yes, good evening. There's no equations. I'm just just to start with the motivation first. I'm going to talk about Folding the World. This is a book that I published in German. It's going to come out in April in English. This is how the cover's going to look like. But I've been growing up basically in an institute for 22 years now at the Potsdam Institute for Climate Impact Research, where people really feel very strongly about the climate problem, and especially the young people are seriously worried. The old people are too, but we are faster out, so it's a bit of a different situation. However, the young people feel that we have to actually reduce the impact of human beings on the planet, and that is true, but it very often feels as if the only two narratives that exist are the one that says we have to continue with our growth in exploitation of this planet, and the others are going to say we have to go back and reduce what we are doing on the planet. I think that we need a new narrative, and the folding of the world is my suggestion for this new narrative. You can see it here illustrated at the back, but let me first tell you something most of you will know, but let me tell you in my own words why we need a folding limit, especially with respect to climate. It'll be later also applied, this concept, to other parts of society, to the size of companies, our sovereignty as humans and as states, and so on and so forth. But let's start from the beginning. It sounds epic, right? Anyway, I'm trying to keep you interested. When I was 5 years old, this doesn't work, so let's do it this way. This doesn't work either. I have this kind of problem. I don't know why I cannot. Here we go. So this starts at least, but I don't know how I can. Oh, here we go. When I was 5 years old, a British glaciologist, John Mercer, published a paper in Nature. And as you know, Nature is not just any journal, it's probably the highest ranking, or at least one of the 2 highest ranking journals on the planet in all natural sciences, and increasingly also in economics and social science to a certain extent. John Mercer made a number of, so it's not an opinion piece, that's what I'm saying, it's a scientific article. And in 1978, John Mercer made a number of statements already in the introduction. He said, if we continue to emit carbon at the rate that we are currently doing, then we'll have doubled the amount of CO2 in the atmosphere over a period of 50 years. That wasn't very deep. I could have done that, I think. Not at the age of 5, but it was simply extrapolating what he saw into the future, and generally physicists feel that they can do better than just extrapolating. Anyway, it turned out to be true. We're not quite there yet, but we are on the path of doubling the CO2 on the planet. But this was only in the introduction. What he said then, still in the introduction, was the warming that will be caused by the CO2 will lead to a warming of the ocean around Antarctica. He was a glaciologist after all, and he said then what will happen is the ice shelves in the Antarctic Peninsula will disintegrate. And in 2002, it was the last B ice shelf, which was the first ice shelf to ever make it to the front page of the New York Times, because it disintegrated over a fortnight, over 10 days actually, into small pieces. This was, as I said, still in the introduction of the paper. The 4-page paper was actually about the stability of the Western Arctic ice sheet. Now, I call this always in physics we trust, because on the American dollar sign there says in God we trust, and I'm just advocating that physics works quite well too. In some occasions, in other occasions you might use of other means. But physics has a remarkable predictive power, and that is shown by the fact that what John Mercer predicted back then turned out to be true. In May 2014, on a Monday, there were 2 papers coming out by Ian Jogwin and Eric Regnault from the States, which supported another paper from France, from Fravet, who all said that the Western Arctic ice sheet has now been destabilized in Amundsen's sector. Now, mind you, John Mercer didn't have computers to do this prediction. He didn't have satellite data. He just had a little bit of data on the topography of Antarctica from, expeditions with dogs and these guys. I'm just imagining it. But what he had was physics. He had the equation, the Newton equation, applied to the ice sheet, and he made this prediction. He said that there would be an instability, and with instability, physicists mean something different than the rest of the planet. I learned this on over the decades. What we mean by that is that if you have perturbed your system to a certain level, and then even if you don't perturb any further, the system generates a self-amplifying feedback that makes it tumble into a new state, to a qualitatively different state. Some people call this a tipping element or a tipping point. The point is it's an instability. And we turned on, we went to Alaska and took from Fairbanks the ice sheet model that was developed there and developed it further for Antarctica. It's now the most used ice sheet model on the planet, and we're very proud of that. So what we did was we destabilized the West Antarctic ice sheet in Amundsen's sector, and with enormous computer power, we looked what happens to the Antarctic ice sheet if you destabilize it there. And what happens is exactly what John Mercer predicted, namely it discharges all its ice into the ocean and elevates sea level by 3 meters, 3.5 meters. Now, mind you, this is kilo years. That's a funny talk for thousands of years. So it'll take a while to unfold this kind of tipping, but it's inevitable because it cannot be undone. There are some people who try to find techniques to undo it, but I'm doing this here to illustrate the predictive power of physics. You can have a similar situation in the Eastern Arctic ice sheet, and there you have another 3.5 to 4 meters of sea level rise waiting to be initiated. Why I'm saying this? Well, we have now a full stability analysis of Antarctica. This was the cover page of Nature a few years ago, and we know where the instabilities are lying and where how much ice will survive at what level. We know that sea level is rising. We know that a higher sea level wouldn't be a problem, but a rising sea level actually is a problem because we've built infrastructure near the coast lines. This is a nuclear power plant in Scotland. The brewery Guinness has a has a contract for their real estate for the next 5,000 years, and I can promise you they will not keep this contract because Dublin will be underwater. Sea level rise is increasingly rising, so it's accelerating, as you can see here. And all of this just to tell you that sea level rise is a problem on the one hand. You can see here the amount of sea level rise that we will end up with per degree of warming is about 2.5 meters per degree of warming, which means that if you give up the Paris Agreement, if you pass the 2 degrees of warming, you will end up with at least 5 meters of sea level rise, which means no more Shanghai, Calcutta, New York, New Orleans, and Hamburg, for that matter. Germany is always really small in cities. Yeah. The UNESCO World Heritage will be underwater, but all of this is not really the point of my talk. I just want to tell you, in physics, we can trust. The physics of sea level rise is very simple. Ocean water takes more room when it gets warmer, and ice melts when it gets warmer. Similarly fundamental, even though a little more complicated, but similarly fundamental is the physics behind the global warming that we are seeing. And let me very briefly emphasize why a theoretical physicist like me is standing for 22 years and on stages like this and telling you that global warming is a real thing. It's not because of any kind of correlation. It's not because CO2 is going up and temperature is going up. Oh, they have to something to do with each other. It's because we understand the problem fundamentally. And I really want to emphasize this because at the moment on the planet, there's a backlash where people start to think again that climate change might not be caused by humans and the climate change we're observing. But let me run you through this very briefly. From quantum mechanics, we know what molecules like CO2, CH4, methane, and nitrous oxides are doing with light. We know the absorption and emission spectra of these molecules. This is not a climate science thing, it's a physics thing. It's depending on where you study, you have this in first semester and third semester of physics. And that shows you that, well, you can't see CO2, which means that it's basically, visible light is just going through it. And the sun is very hot, so it's emitting mainly visible and UV light, and this light is just going through the molecules unstopped to the ground of the Earth. And the Earth is then warming up to a certain level, but obviously the Earth is much colder than the sun, so it's emitting in a different frequency spectrum, mainly in infrared. And this is where the absorption and emission spectra of these molecules lie. And from this radiative effect, from pure quantum mechanics, which you can compute with pen and paper, you get 1.1 degrees of global warming for every doubling of the CO2 in the atmosphere. This was already computed 110 years ago by Svante Arrhenius, Nobel Prize winner from Scandinavia. And this 1.1 degrees for every doubling of the CO2 wouldn't worry us too much. But then there's the first feedback in the climate system that kicks in. And that's something that all of you know too, and you can prove it every day if you stand in front of the mirror and just breathe against it. That's the Clausius-Clapeyron equation of 1834 that tells you a warmer atmosphere can hold more water vapor. So the 1 degree that you get from quantum mechanics, it means 7% more water vapor in the atmosphere. And water vapor, H2O, is again a greenhouse gas. You go back to quantum mechanics and you get another 1.5 to 2 degrees of global warming for every doubling of the CO2 on top of the degree that you had before. And you end up with the climate sensitivity that we've been working with for a long, long time now and which we're proving over and over again with different methods. 3 degrees Celsius of global warming for every doubling of the CO2. And this is the basis that we stand on and that we cannot avoid. There are clouds, there are all kinds of different things that kick in that make the world more complicated, but we can't get around this basis of 3 degrees for every doubling of the CO2 in the planet. And that means that the CO2 emissions matter. We have different paths into the future. This is the so-called, it was called the business as usual path for a while. It's called RCP 8.5. The blue one here is 2.6. You don't have to keep this in mind. I just show you these are the CO2 emission paths that we can go into the future, and they translate into temperature paths. The red one will bring us to 5 degrees of global warming. Looks like 4, but it's not 4. It's closer to 5 because the reference here point is not pre-industrial, but something else. And this one is the one that keeps us below 2 degrees of of global warming. This is really not important. I just want you to remember red is warm and blue is cold. What I think is actually very important, and I'm mainly talking to industry these days. I'm either talking to scientists or to industry. These are the two groups that I talk to. And whenever I talk to them, I tell them this is the only thing you need to remember from my presentation. And let me briefly walk you through this. What you see is 3 panels. On top, it's CO2 emissions for 3 different scenarios. In the middle, you have the first response, and that is the CO2 concentration in the atmosphere. That's the amount of CO2 that you actually keep in the atmosphere. About half, for a while it was half, now it's about a third is going into the ocean, and it's generating problems there. But the other part is what we have in the atmosphere. That's the CO2 concentration here. And the lowest one, and I'm sorry for the German here, I should really change that, I'm sorry. And the last one is the warming that you get as a result from that. You have 3 different lines in these graphs. The small one, the dotted one, is the one that keeps the Paris Climate Agreement. It keeps us below 1.5 degrees. The dashed one is what you get if you burn on the business as usual path until the end of the century, and then you do climate protection. Then you end up with 5 degrees of global warming. And the solid one is if you burn everything we found. All oil, all gas, but especially all the coal, because coal is the big player on the planet. Then you end up with 15 degrees of global warming. This is consistent with the time when the dinosaurs were on the planet 100 million years ago, the time when the CO2 actually was taken out of the atmosphere and buried underneath and became oil, gas, and coal. So it kind of makes sense. I mean, there's more to it than that, but I just want to show you that we also understand paleoclimate to a certain extent. But this is not, the difference in the lines is not my point here, actually. The point of this graph is actually here on the lower left. This is the year 2000 of the Common Era, and this is the year 4000. We've actually, in the publication, drawn it all the way to 12,000. The CO2 is going down very, very slowly. It's not the CO2 that we breathe out. This one was recently taken out of the atmosphere by photosynthesis, either because you're eating directly the plants or you're eating beef and they ate the plants before, the cows ate the plants before. But it was recently taken out of the atmosphere. The CO2 that we are creating by burning oil, gas, and coal hasn't been in the atmosphere for 100 million years. And that's why it doesn't have a sink. It stays in the atmosphere for very, very long, for hundreds to thousands of years. For any practical purpose, it stays in the atmosphere forever. And the warming goes down even slower because we are currently creating a heat bath. We are pumping most of the heat, 97% of the heat that we are trapping on the planet additionally is going into the ocean. So we are warming up the ocean, and this heat bath will warm us for a long time, so the temperature is going down even slower. The most important conclusion from that is the following. No matter where you want to stabilize the temperature of the planet, whether at 1.5 degrees, at 2 degrees, Paris Agreement, 3 degrees, 4 degrees, 5 degrees, no matter where you want to stabilize it, you have to get to 0 emissions. And whenever I say this to industry, it's like, the room gets dark, right? Because they think, I can see them thinking, oh, we got the worst climate scientist of them all, right? We knew there was a climate scientist coming, so we knew you had to reduce CO2 emissions, and this one's saying 0, right? But then after like 30 seconds of thinking together, they realize 0 is much better than less. Because you cannot go to industry, you cannot go to an economic market-oriented person and say reduce, do less. But if you say 0, they realize we don't have to do less, we have to do something different. So we have to fold our trajectory into a different direction because we live in more than one dimension. And in this particular case, the other dimensions is the opportunity space on the planet. So this is the main narrative that I'm trying to offer. It says we have limits, we have borders, we are living on a finite planet. So let's accept the limits and let's set them strongly and allow competition to find innovation to find new paths. Some of these paths might be simply changing the way you live, changing the way you consume, changing the way you use energy. Other limits might be, other innovations might be changing of technologies and so on. So this is a direct conclusion. No oil, no gas, no coal eventually, if you want to stabilize the temperature of the planet. And let me briefly motivate why we should do that. This is the death curve of the coral reefs on the planet. This is the temperature on the x-axis, and this is which percentage of coral reefs on the planet will be dead. At 1.5 degrees, which we passed last year, basically all coral reefs on the planet are dead. 600 million to 800 million people worldwide depend with their livelihood on coral reefs. Permafrost is thawing in Canada and Siberia. This is generating biological activity without O2, without oxygen, which means what they create, this biological activity, is CH4, is methane. It's another greenhouse gas, very potent greenhouse gas, which is getting into the atmosphere. This is not even covered in what I showed you so far. The Arctic sea ice is melting dramatically and amplifying the warming near the North Pole, which I will show you in a minute, has direct influences on weather extremes in the Northern Hemisphere. This is a satellite picture from 1979. Mid of September is always the end of the melting season, so this is the minimal extent of the year, and this is 2022. There was no hole in the ice in the North Pole, it's just no data. That's just, well, clear this up. The Arctic sea ice is going down dramatically. This is the last 1,450 years, and we see the sharp decline in recent decades. The Arctic sea ice will be gone in summer in 20 years, no matter what we do. Now, why do we care in Abu Dhabi for this? Well, I'll tell you in a minute. It's because of weather extremes. I've talked about sea level rise. I've talked about the inevitability of increasing the temperature of the planet if we increase the CO2 concentration. I've talked about things where we change the planet on a large scale. But what really is the important thing for us now are the weather extremes. And we've tried to understand weather extremes first with statistics, and that works every now and then. That works for heat waves, for example, quite nicely. You can see here the heat wave in 2003 compared, this is the death rate in Europe for different years, and you can see the COVID pandemic here in 2020 and the heat wave in 2003. This was like 60,000 additional deaths. So we can understand heat waves with statistics. They're particularly important in the tropics, right? A heat wave in Europe is one thing, and a heat wave in India, a heat wave here is a different thing, because if you have a lot of water vapor in the atmosphere, you cannot cool yourself by sweating, which means that you end the level of adaptability, or you end the level of where you can still adapt, or we can survive very quickly. So if the so-called wet bulb temperature goes above 35 degrees, you simply die. As I said, heat waves can be captured by statistics quite nicely. This is the European summer temperature, and the median is taken away, and then you have here the first standard deviation, the second standard deviation, the third standard deviation, which means that this is a 1 in 100 event. And let me just briefly, this is the observed shift in the temperature, right? And it's only a very mild shift to the right. It's, as I said, 1.5 degrees globally, which means in Europe 3 degrees, double the amount. But look what happens with extreme events. They increase quadratically exponentially simply because the curve is a bell curve, is a Gaussian distribution, right? This is something we really have to appreciate, and this is basically how fast can we adapt, and where's the limit of our adaptation that I mentioned earlier. Climate change is not going to be a big wave that kills us all. It's not going to be like smooth, like in a Hollywood action movie where the bad guys die at the end. It's going to be pressure on our systems. The 3 years before the Syrian crisis, the beginning of the Syrian crisis, were drought years in the region. They didn't cause the situation, but it certainly doesn't help when you have a drought in the region. And that's basically something that we have to appreciate. This is how climate change will act on us. There are nonlinearities in the climate system. The water vapor goes up exponentially. We have tipping points and so on and so forth. But the big instabilities lie within our societies, most likely. When we go to extreme rainfall events like you had a few years ago, like last year, I think, in the region in which we are observing more and more on the planet, statistics helps a little bit, but it's actually better to understand the problem fundamentally. And we can do so by the Clausius-Clapeyron equation that I already mentioned. You know, Clausius-Clapeyron, they found the equation in 1834. Clausius actually found it in 1850, this was good times when you could be a co-inventor of an equation with 15 years in between, right? This was when information flow was much slower. So as I said, a warm atmosphere can hold more water vapor, and the amount of water vapor that you can store in the atmosphere is determining how strong extreme rainfall events become. People, when they think about global warming and rainfall, they think about evaporation from the ocean. And that's true. The amount of water that evaporates from the ocean is increasing by about 1% per degree of warming. And this is also how much the overall rainfall on the planet is increasing, because everything that goes up has to go down somewhere. But extreme rainfall events increase much stronger. They increase with 7% per degree of warming, because this is how the Clausius-Clapeyron equation tells us how much you can store in the atmosphere. It's a very different thing. If you have to ask me later if you want this explained a bit more. But it's interesting, and we can see this is actually working. You see here the Clausius-Clapeyron equation in action. This is the dashed curve here. This is the warming, and this is in different models the increase of extreme rainfall events, the intensity of extreme rainfall events. The models scatter around because there is still also more than just the Clausius-Clapeyron equation at work, but they scatter around this curve quite nicely. 7% per degree of warming, 6.5 in the models. When you look at the frequency of extreme rainfall events, it's a different picture. You can translate the Clausius-Clapeyron equation into frequency of extreme events, and then you can end up with 17% more rainfall events, extreme rainfall events for every degree of warming, and the models can't do that. The observations are quite nicely scattered around, in different places on the planet. They're quite nicely scattered around the Clausius-Clapeyron prediction, but the models, they average out large parts of that would actually have an event, and then that's why they underestimate the frequency. All of this to tell you, in physics we trust, and we know why extreme heat and extreme rainfall events actually increase under warming. Let me very briefly amplify this a little bit by telling you about the jet stream, because I really like it. It's going to take a moment, but it's very interesting physics. And what you were looking at the moment was a moment ago was the North Pole, and this the red wind band that you see here is actually the jet stream. It's a wind flow around the planet. We'll restart it in a second. You can see here, this is the North Pole, this is Greenland, and now you have the jet stream here. Now the jet stream is important because it exists because the Earth is rotating, and this was not going to change anytime soon. But the position of the jet stream is important because north of it there's dry, cold Arctic air, and south of it there is moist, humid tropical air. And the stability of the jet stream is very much determined by the temperature gradient of the North Pole and the tropics. And we've just seen that the Arctic sea ice is melting like crazy. So the temperature gradient, that's one of the two reasons why the temperature gradient between the high latitudes and the low latitudes is declining. And we see more and more often these kind of meandering of the jet stream, this wavy kind of lines. And whenever that happens, bad things happen. In 2017 and also 2018, the US from Chicago to New York was covered under 2 meters of snow because the jet stream had meandered to the south, cold Arctic air getting into the moist tropical air, and a lot of snow occurred. A month later, something happened that no one really realized on the planet because it happened in Siberia, and there are much fewer people living there. But in Siberia, the temperature, over a period of only 5 days, the temperature increased by 55 degrees. Celsius. That's 110 in Fahrenheit, roughly. That's I double. Well, I'm sorry. If you had this in a metropolitan area, you would most likely had the hospitals filled with people who couldn't stand this kind of temperature shock. Another month later, Berlin, where I come from, was 10 degrees colder than the North Pole. The North Pole hadn't seen any daylight for 3 months and should be at minus 20 degrees. But the jet stream had meandered so far into the north that it had actually torn off. And a little eddy was created with tropical air in the middle. And it was wandering around the Arctic and melted the North Pole. It didn't melt it all the way. It just brought it to zero. I'm telling you this because we see this kind of effects all the time. This is Denver, Colorado. 35 degrees temperature drop in 24 hours, 33 degrees on one day, minus 1 degree the next day. This is the kind of hits that we expect under global warming to intensify, not just because of the thermodynamics that I told you, but also because of the dynamics. The jet stream has another very exciting phenomenon, very interesting phenomenon, and I'll just very briefly tell you about this. If these kind of wavy lines here, if they have exactly one of 5, 6, or 7 of these bellies, when you go once around the globe, the pattern stops. The wind is still blowing within the band, but the pattern stays the same. This is what happened in 2010, where Moscow had to be partially evacuated because of wildfires that wouldn't stop. And at the same time, Pakistan was flooded so badly that the greatest freshwater lake on the planet was created, and 10 million people had to be evacuated from their homes. 10 million people. We see this phenomenon now in 2019 in Europe, and let me briefly show you this. These are the 7 hills that I mentioned, 1, 2, 3, 4, 5, 6, 7. Whenever that happens, it's like you take a rope and you attach it to a wall and you create a pattern that doesn't move, that's just going up and down. That's a standing wave. Whenever you have a wave number 7, as here, the wall are the Rocky Mountains. So the Rocky Mountains stabilize this situation, and then you have droughts simultaneously in all the 3 major wheat-producing areas on the planet. We had this in 2019. It wasn't long enough so that we had a food crisis, but this is something that can happen in the future. All of this to tell you tropical storms are increasing. Let's not talk about it. The economics is affected, obviously. Economic growth is affected, and that's very important, and that shows you that the economic optimum is at 2 degrees of global warming now. But all of this to tell you that it's worthwhile to stop warming the planet. We have to do it anyway. We cannot go to 15 degrees. We have to do it anyway, so let's do it rather sooner than later. And the only way to do it is to set a hard limit to 0 carbon emissions. I know this always sounds strange. To some it does, to some it doesn't, but actually it only doesn't sound strange to people who have heard it before. So we are in a dilemma. Basically, all of my students are vegetarian or vegan, at least vegetarian. I'm the only one who's eating meat on the table and at lunch in my institute, which doesn't make me, it's difficult. Let's put it this way. But why I'm saying this is, if you look at the growth rates of GDP, of gross domestic product, and of all the different exploitations that we do on the planet, they are all increasing exponentially. The GDP is going exponentially up, and so does the usage of raw materials, the CO2 and so on and so forth, the energy consumption. So it's a reasonable thing to say, well, we have to stop the growth. There cannot be infinite growth on a finite planet. This is a conclusion that you hear over and over again. But then you have the dilemma that we still have to develop. There's so many poor regions on the planet. We have to redistribute wealth potentially, but we also have to still develop. We have to develop in Europe. We have to develop in the US. It's something that we can't do. We can't stand still. We have to continue developing. So how can there be actually, is that a dilemma? Well, it's very simple, and this is what I told you about earlier. I could be bounded in a nutshell and count myself a king of infinite space. That was meant differently by Shakespeare, but I kind of captured it. We live in more than one dimension on this planet. We have an opportunity space, and we have actually introduced these. Sorry, this doesn't work, obviously. So these are the equations of what you saw earlier. It's just for fun. These are the only equations, and you don't need to know them at all. So we need to introduce hard limits, and I would advocate that introducing hard limits is actually much better than just perturbing and annoying the system, slowing the system down. That's what we're doing in Europe for a while already with a number of environmental regulations. People hate regulations increasingly because it feels like they're just annoying. They're just disturbing you while you're going forward, and they don't tell you you shouldn't go there, just make it less good, right? But if we set a limit and say you can't go there, find another way, that's a different issue. Then you're not being slowed down. Your innovation just is redirected into a different place. And we've done this in the past. We've introduced what I'm now calling folding limits. The first one that I would always want to mention is the introduction of private property. Now that doesn't sound like a limit. It's a right, right? You have the right for private property, but it was actually a limit to the mighty. It was a limit to the king or the lord of your region that they couldn't take away what was yours. Even if they had more power, if they had an army or if they had the weapons, they weren't allowed to do that because it was yours. So it was a limitation that we set at one stage in history, and there are much better people to tell you when this happened and where in different places. I just want to go as far back as my imagination carries me. The Declaration of Human Rights was another of these folding limits. These were put out by moral and ethic considerations, right? We did this because we thought it's a good idea that you cannot treat another person badly, that you cannot discriminate against other people. We're still struggling with these and all over the place, but we have put this as an aspired goal for our work, for our life. The third one, and this is quite a leap, I'm aware of that, but I need to get to reality, to the present of what we're talking about quickly, is the European Carbon Trading Scheme. And for those of you who don't know how this works, in the European Union, we put a price on carbon to a certain extent, but we didn't just put a tax on carbon, which means that if you want to emit carbon, then you have to pay a price for it. We did it in a slightly different way. We give out certificates for emitting carbon. And if you want to emit carbon, if you want to burn oil, gas, and coal, then you have to have a certificate like this. And then we just say transparently and openly, these certificates will become less and less until they are zero. And a few years ago, it was meant to be zero in 2058, and 2 years ago, they shortened this to 2039. Now, what I'm arguing is this is a nice way to introduce a folding limit, because it's not just annoying people by making it expensive to burn oil, gas, and coal. It says in 20 years you can't do it anymore. And you can gain money now, you can actually earn money now if you are faster in reducing your carbon emissions than your competitor. So it's generating innovation, it's redirecting our attention towards innovations into other directions. In the same time when this was sharpened here, we also started discussion on ETS2. This is the emission trading scheme for buildings now and road transportation. This is not fully implemented yet, but it's meant to be at zero in 2045. And we also introduced, and I'll come back to this in a minute, the so-called carbon border adjustment, which means that if you want to import something into the European Union, you have to, and which was produced using CO2, you have to buy the CO2 certificates in the European Union in order to do so. This is what some people call the supply chain law. We have a supply chain law in the European Union also that was introduced by a Conservative Party member, actually, and this was also done by a Conservative party. And I'll talk about this as the last folding principle in a minute. But let me continue and show you where this path might be leading. I think we can have infinite economic growth on a finite planet, because the GDP just is supposed to tell us something about our welfare, of our livelihoods, and how good the livelihoods is. They're supposed to be associated with our well-being. It's probably not anymore, but it's supposed to be like that. And as long as it's just a number in a computer that reflects a societal consensus that this is worth something, that you can buy something with it, it can increase infinitely. It's just a number in a computer. So infinite growth, economic growth on a finite planet is possible. What's not possible is infinite exploitation of raw materials on a finite planet. And that is that's a physical fact. We don't have to argue about that. That's a physical fact, and eventually it'll kick in. Now we can see this already with plastic. It's not a good idea to have plastic. Plastic is similarly abundant in the world. Similarly has a long lifetime on the planet as CO2. So I think that the way we are dealing with carbon in the European Union, it might be a blueprint of how to phase out other things that we eventually need to get rid of, like, for example, plastic. Eventually, we will have to do this for all raw material exploitation. But I want to invite you to briefly think about this. That just means that we have to produce in such a way that we can reuse, or we can use things that regrow. That's all it does. Because the only thing that is actually always coming newly onto this planet is energy. A lot. So you can get around the second law of thermodynamics. This can actually work because we are an open system. And last but not least, there's two more folding limits. I have a third one which I'm not going to talk about. It's in the book, but but this one is about the sovereignty of the people. That is especially important for democracies, I guess. We have once said that we want to that the people are supposed to be the sovereign of the country. Now, what happens if a company gets so big that it's comparable to the size of the budget of a country, for example? Well, society could decide that no company is allowed to be bigger than the state it's operating in. I'm not saying we should, but it's what would happen? Well, a company, if this is the limit of what we say it can be, let's say 500 billion or something like this. That's the annual budget of the Federal Republic of Germany, but you can pick another number if you like. Now, a company will grow, and it will grow, and then it gets towards the limit. And if you do this with a corporate tax that goes asymptotically to 100%, then what will actually happen, the stakeholders will say, well, we're not going to pay this kind of taxes. We just split up the company into pieces. And then the governmental authorities just have to check whether these are actually independent companies. And what you do is you actually increase competition. You go back to a better market than you were before. This is actually done at the moment with agencies on a basis that is, takes forever. It has to go in the US. It has to go through the Senate, and in Germany, it's a big thing. For example, this agency in Germany, the president of this agency, a few years ago said, after 10 years of research, we have concluded that Google has a monopoly. It's not their fault. They have to do this properly, but you have to incorporate this into the dynamics. And what will happen is it won't be the end of market economy. It'll be a renewal of market economy because it increases competition at a certain level. And now I want to come back to this question of sovereignty of countries. In Germany, in Europe, I know there's always this discussion. If we increase things that are negative for companies, they'll just go elsewhere, right? This is a common thing, and what it does eventually, it takes away the sovereignty of the country. We cannot do the laws that we would like to do because we have to be afraid that they move out. Now let's talk about a generalized supply chain law, and let me just propose one, and that will be the end of the talk, and then you can ask questions if you like, or you can just go. What if we decide that within a governmental entity, like a country or the European Union, where you have actually, you've agreed to a government and a set of laws, only products can be sold that have been produced following the laws of the country, of this governmental entity. Whenever I say this, it sounds so obvious to me that this should be the case. It's a very, right? We're far from this. We're really, really far from that. And I think these kind of limits can actually be introduced in countries without, well, they can be. We probably need some time to do this adjustment, but I think we need a new narrative to go into the future, and folding the world is my suggestion. Thank you.